Hi class, today I am covering combustion and empirical formula and as well as molecular formula. This is the last section in chapter 3 and I am going to provide some more information to help you understand this section. In combustion analysis, empirical molecular formulas for compounds that contain only carbon and hydrogen. These are organics. If you go into organic, everything you study will be carbon and hydrogen. Or carbon, hydrogen, and oxygen as well. So when you deal with combustion analysis, you'll either deal with strictly carbon and hydrogen, which are called hydrocarbons together, or carbon, hydrogen, and oxygen. And these can be determined with a process called combustion analysis. The compound is weighed before it's analyzed, and then it's placed in an apparatus and burned completely. The only products of the combustion, a combustion reaction, remember, produces CO2 and H2O as the products, which is exactly what's going to happen here. So only the products of the combustion of a compound that contains only carbon and hydrogen, or carbon, hydrogen, and oxygen, are carbon dioxide and water. Same as combustion reaction we covered is exactly what I said. Assume that all the carbon in the compound has been converted to CO2, and then we calculate the mass, which is what I'll show you later. Assume that all the hydrogen in the compound has also been converted to H2O, and we'll work on that one as well. If the compound contains oxygen as well as carbon and hydrogen, then we're going to calculate the mass of the oxygen by subtracting the mass of the carbon and hydrogen that we'll determine. Use this data to determine the empirical and molecular formulas in the usual way. So the steps don't change once you can break this down. So here's a very quick overview of an instrumentation, some instrument that would allow this to happen. O2 would be in the sample. It would go through a water absorber and a CO2 absorber. And the mass gained by each absorber corresponds to the mass of CO2 or H2O produced from the original sample that contains carbon and hydrogen. So compounds like C, H, and O are routinely analyzed through combustion in a chamber like the one above. C is determined from the mass of CO2, and H is determined from the mass of H2O. And if there's oxygen, then we would also determine that subtracting the mass of carbon and the mass of hydrogen. So here's just a setup I found to help you understand that there's certain steps that pretty easy to follow, and they really don't deter off of this. There might be some small inconsistencies somewhere, but they really don't change. You have a sample mass that's provided. This is the mass before the combustion happens. And then, so I just label it X, Y, and Z because we don't know the formula, which is what we're trying to figure out. Then you are also provided in the problem masses of CO2 and H2O. These are the masses that are provided after the reaction occurs. So between what you start with and what you end up with, we can figure out the mass and the moles of carbon and hydrogen. Once we get the masses of both of these, then we can subtract oxygen from the original sample, and that will give us our mass, and then we can change that to moles. Once we get the moles, then we can divide by the smallest value, which will give us empirical. And if you don't have whole numbers, you can use multiplication on everything until you do. And if you are given a molecular mass, then you can also continue on to determine your molecular formula, which is our last problem. So combustion analysis, isopropyl alcohol, a substance sold as rubbing alcohol, is composed of CH and O. Combustion of 0.255 grams of isopropyl alcohol produces 0.561 grams of CO2, and sorry, my alarm, and 0.306 grams of water. Determine the empirical formula of isopropyl alcohol. So for me, I'm a very visual person. It helps to keep things in a way that I can see what I have and what I need to do. So what I do is I just put a generic combustion reaction up. It's not the greatest, but it's a point because we're missing a gas here. But it's a generic for me to see the values that I have. So what I have here is, and you can put O2 if you needed to here, but I have my compound that I don't know the original sample ratios are. And then I have my carbon dioxide, which was produced, and I have my mass of water. So by seeing these, it lets me see what I have to work with. First thing is you start with carbon, easiest one. Grab the carbon, and then you see the amount that you're given, and you're simply going to do dimensional analysis stoichiometry to determine the mass and moles of C. So that's what we do. We take the molar mass. 1 mole of CO2 is 1 mole of CO2 to 1 mole of C. Now you would stop here and get your moles number if you wanted to, and then proceed to get your mass. So I give you a point of where you can stop on these. So here we have our mass of carbon from this compound. Now we're going to determine our mass of hydrogen. So we take the mass that's been given to us from H2O, and we do the same thing. You would stop here if you wanted your moles of hydrogen, and if not, you would go on. So here we have our mass of hydrogen. Now, our sample, which is here, we're going to subtract these to get our mass of oxygen, and that's exactly what we do. Take your original sample, subtract your carbon mass and your hydrogen mass, and that leaves you with your oxygen mass, which is now everything we need to proceed to determine our empirical formula. So here, I just highlighted the main parts that we need, and I didn't do the moles. I did it elsewhere, but you can see that with this, I determined the moles of each one of these. So now we set it up where we can, oops, this isn't supposed to be underlined. You divide each by the smallest value, which is what we did. And when I did that, I end up with 3, 8, and 1. So my empirical formula is 3, 8, carbon, C3H8, and oxygen. So this is not a difficult problem, especially if you understand how to do empirical formulas. There's always the same routine. It really never changes. We have one that takes an extra step now, where it's asking for the molecular formula. This one is a little wordy, and that tends to be a sign it's a combustion problem or empirical formula. They tend to give you a lot of information. I don't know how to say this correctly. Dianabol is one of the anabolic steroids that has been used by some athletes to increase the size and strength of their muscles. It is similar to the male hormone testosterone. Some studies indicate that the desired effects of the drug are minimal, and the side effects, which include sterility and increased risk of liver cancer and heart disease, keep most people from using it. The molecular formula of Dianabol, which consists of carbon, hydrogen, and oxygen, can be determined using the data from 2 different experiments. So I highlighted or bold-faced what we need to use. In the first experiment, we have an original sample, which is 14.75 grams of Dianabol. It is burned, and from that, it produces 43.257 grams of CO2, 12.395 grams of H2O are produced. In the second experiment, the molecular mass of Dianabol is found to be 344 grams. There should be a G there. What is the molecular formula for Dianabol? So the first thing we need to do is determine the empirical formula. And then with the empirical formula, we're going to use this molecular mass. And that's going to provide us with the molecular formula that we need. So I have everything. I found this from another site, and it's kind of weird. It like cut off on their page. I didn't do this. But let's go through so you understand that the steps are all the same. This one's just not as broken up the way that I did it. But here we have our carbon. So we're going to determine the mass of carbon. So we take our CO2, break it down until we get our grams of carbon. Same thing with hydrogen. We want to determine hydrogen. So we break that down until we get our grams of hydrogen. Then you take your original sample mass and you subtract those, and now we have our mass of oxygen. So the next thing we need to do is determine our moles of carbon. So in this case, they took these masses here and then just determined the moles. So that's what you see here for all 3. We have our moles of carbon, moles of hydrogen, and moles of oxygen. They did an extra step here of just dividing by the smallest value, which they determined to be, and I don't agree with them, but I guess it's so close. No, it is. Sorry. There's a 0 here. I was looking at this one and this one. There's a 0. So this one would be the smallest. So they divided everything by the oxygen mole ratio, and that gives 10 mole of carbon, 14 moles of H, and 1 mole of oxygen. So when they put this in the empirical formula, it's C10, H14, and O. Now there's one more step here. There's a formula that's given to give you the rate, the multiplier is what they call it. And this N is the multiplier, which is what we need in order to determine the molecular formula. So we were given the molecular mass of Danable, which is 300.44 grams. So that's what they plugged in here. That's what this extra second experiment was used for, is to determine the molecular mass. We just don't know what the molecular formula looks like. So we put the molecular mass, and then we add up everything here to determine the empirical formula mass. So this here is saying that when added up, it equals 150.22. Divide that, and it gives us 2. So now we take this 2, and they don't show it specifically in this one, but you take this 2 and you multiply every subscript by that 2. And that is going to give you the actual molecular formula of Danable, which is C20, H28, and O2. If you have any questions on this, please contact me, post on Pronto. We can go over anything here that does not seem clear. Thank you.